Hello and welcome to our next module on convolutional codes. Let's start with a brief outline for today's talk. We would discuss what we mean by tree codes and convolutional codes, followed by the notion of trellis codes. This is an interesting class of codes with memory. Then we will understand how we do encoding using trellis codes, and finally we look at the polynomial description followed by the generator polynomial matrix specifically for convolutional codes. So, that is the brief outline for today's talk. Now, let us see what we have done so far. So far we have looked into different kinds of linear block codes, including cyclic codes, BCH codes, Reed-Solomon codes and several other examples, but they were all codes without memory. What we want to do today is look at a different class of codes with memory. So, the block codes that we have studied so far always had a one-to-one correspondence between what is the input information block or the information word and the output word or the code word, always. So, if you have the same information word coming in, you would always look up in the lookup table and give out the same code word, right. So, this is useful for high data rate applications, and the incoming stream of data is broken up into blocks. Each block is encoded, and we have seen very good codes like Reed-Solomon codes with beautiful distance properties and very efficient code rates. Now, the large block lengths also suffer from a basic disadvantage. Even though they give you very efficient codes, we cannot declare the results of decoded output until the entire block is received and decoded. So, we cannot start declaring the results. So, if the block consists of say 1024 bits and we are working at 10 kilobits per second, then there is a tangible amount of delay possible before we start declaring results, and this may not be very conducive for real time operations. But there is another class of codes that we are going to study today where the delay is minimal, and that what we will study is the convolutional codes today, which works using information frames of length k naught, which are in just a few bits. So, please note, earlier the k, the information word, used to be 253 bits or 473 bits. They are large or even thousands of bits long, but here the information frames that we will deal with will be just a few bits, 1, 2, 3. So, we will be working with much smaller sets of symbols which will be used to encode, and each information frame would result in a code word frame of length n naught. So, what we are doing different is k naught symbols or bits will be encoded into n naught symbols or bits, where both k naught and n naught are small. So, we would have not just the usage of the input frame, information frame, to generate the code word frame, we would also use memory. Okay. So, we would use the stored information of previous m information frames, and we would together use the current frame and the previous m frames to declare what is the resultant code word frame. So, it should be obvious that the same information frame may not lead to the same code word frame because we do not know what is sitting in the memory. So, let us talk about codes with memory, right. We have mentioned that previous m information frames are used to obtain a single code word frame. So, we are going to rely on memory, right. So, such codes which are based on this memory and obtained in this fashion are called tree codes. A subclass of tree codes which we will use in real world are the convolutional codes. We will formally define that today, right. Now, up to now the decoding techniques that we have discussed for linear block codes are algebraic and memoryless, But here we have to go one step further and figure out how to decode codes with memory, because it is not just a lookup table. We have to keep track of what was in the memory. So, the state, the memory becomes important. So, we must have a state space diagram to understand how the encoder is working. So, the convolutional codes make decisions based on the past information, and therefore, memory is an integral part. If you look at a block encoder here, you have these information frames coming in of size k and n blocks coming out, but we will have a different structure for codes with memory. So, what we assume is that we have an infinitely long string of incoming symbols, and this is not a bad assumption, because we have an over deluge of data in today's world, and we do not really complain about too many input symbols coming in. So, first we break up this input bit stream into k naught symbol blocks or frames. We will use the word frames to distinguish from the block codes that we have used earlier. Now, each segment, which is called a frame, will be encoded, but the encoder is it consists of two parts: a memory, which is basically a shift register, and a logic circuit associated with it. So, these two are the ingredients that form the encoder for a convolutional code. The memory, which is a shift register, is capable of storing m previous information frames. So, each time a new information frame arrives, it is shifted into the shift register, but in order to do so, since the size of the shift register is limited, the oldest information frame has to be discarded. Only then it will make room for the new information frame to come in. So, at any time, m into k naught symbols must sit in the shift register, which is the memory. So, when a new frame arrives, the encoder computes the code word frame using the new frame and the stored previous m frame. And what do we mean by computes? It uses some kind of a logic circuit to do so. And once the computation is done, the code word frame is shifted out for transmission. The oldest information frame in the memory is discarded because the new frame must be shifted in. And once this operation is complete, we are now waiting for the next frame to come in and continue the process. Thus, for every k naught symbol that come in, n naught symbols go out. So, clearly the clock rates at the input and output are different. Please note, convolutional encoders are very hardware friendly, right? And since memory plays an integral role in this, therefore, the same k naught symbols at the input may or may not generate the same n naught symbols at the output. So, let us now define something called as a constraint length of a shift register encoder. So, the constraint length is defined as the number of symbols it can store in its memory in terms of the input frames that is coming in, right. So, if you look at a general structure for a tree code, it can be expressed as follows. So, let us start on the left hand side. We have the information frames coming in. You have this long stream of input data, say 1 0 1 1 1 0, so and so forth. We first break it up into information frames of size k naught. My k naught can be as small as 1, it could be 2, 3, 4, but whatever it is, we break the input into k naught frames. Now, if you see, this dotted block is the encoder. It has two components: the memory, which is the shift register, and the logic. Logic is pretty much a set of XOR operations. Now, if you look at the shift register here, you will note that there are a certain number of information frames that can be stored in this shift register. And let us say nu equal to m times k naught, where k naught is the size of the information frame. Then the constraint length nu equal to m times k naught. So, it tells me how many previous information frames have been stored in the memory. An intuitive understanding tells us that the larger the constraint length, the stronger my code can be, because I am not relying on more of the past information. Now, once we have this going, then the logic can be used to compute the code word frame n naught. As you can see, the code word frame is longer than the information frame. If information frame is say 2-bit long, then the code word frame could be 3, 4, 5. If the information frame is 3 bits long, it could be 4, 5 or 6. So, this structure generates for every k naught symbols or bits coming in n naught code word frames. So, this infinitely long code words, because input is infinite, so output is infinite, it keeps going, right, is called an n naught comma k naught tree code. It is to distinguish from n comma k block code. So, we use n naught comma k naught, where n naught is the output frame, k naught is the information frame. So, code word frame n naught, information frame k naught, and the code rate will clearly be k naught over n naught, and you can have a more formal definition in terms of the image. So, a tree code is a mapping from a set of semi-infinite sequences of the elements of GFQ, because we are not necessarily limiting us to binary, into itself such that if for any m, two semi-infinite sequences agree in the first m k naught components, then the image will also agree in the first m k naught components. So, let us look at certain other definitions which will be useful to understand the tree codes. First, the word length. So, the word length can be defined in terms of this m. Remember, m was used to define the constraint length. So, m plus 1 into k naught is k, which we define as the word length, and the block length n can be m plus 1 into n naught. So, I can have a parallel understanding of the word length and the block length for the tree code. And code rate is nothing but k naught over n naught, which can be easily expressed as your n and k, the ratio of the word length to the block length. So, let us have some more definitions. So, for practical shift register encoders to work, the information frame length is typically small. There is a major difference from our linear block codes, where k is huge. So, it could be 5 or less, 7s are also common, but we would rather have small k naught. So, code rate of these tree codes are not really close to unity, because if k naught is for example 5, then n naught can be 6, leading us to the best possible code rate of 5 over 6. Okay. We could have 5 over 7, 5 over 8, but then we are making it worse and worse. So, let us now understand what do we mean by a convolutional code, which is actually used in real world application. So, a n naught comma k naught tree code that is linear and time invariant and has a finite word length k given by this is called an n comma k convolutional code. So, we can easily see that the convolutional code is a subclass of a tree code. N naught comma k naught tree code that is time invariant and has a finite word length k is also called as a sliding block code. Therefore, a linear sliding block code is a convolutional code. So, please note we are still in the domain of linear codes. Okay. So, linearity means the all 0 code word would necessarily be a part of it, and sum of 2 code words would also be a valid code word in the definition of code words that we have just defined. Now, let us understand this interesting concept using a simple example. So, here if you see on the left hand side, your K naught is 1, your shift register has 2 bits, and your output N naught has 2 bits. So, it is clearly a rate 1 by 2 encoder with K naught equal to 1, N naught is equal to 2 and M equal to 2. And the logic is as follows: whatever is in this memory, binary addition with the current input, binary addition with the second stored bit gives you the output bit 2, and output bit 1 is nothing but the present incoming bit XORed with the second stored bit will give you this output bit. So, it is very quickly one can calculate the output based on the input. It goes as fast as the hardware circuit, and we know that the typical delay today in current circuit is less than a nanosecond. So, we can have really fast encoders. So, this example takes 1 bit at a time and encodes it into 2 bits, leading to a code rate of 1 by 2. The information frame length is K naught equal to 1. So, for the block length is M plus 1 times N naught, M is 2, 3, M plus 1 is 3 times N naught is 2 is 6. So, the effective block length is 6. Constraint length of this encoder is nu equal to 2, code rate half, as we can say we have already observed, and the clock rate of the outgoing data must be twice the input clock rate, simply because for every 1 bit that is pumped into that encoder, 2 bits must go out. So, the adders are all binary adders. So, binary adders without carry, which is simply the XOR gates. Okay. So, very hardware friendly implementation. So, how does this encoder work in this example? So, basically we assume that the initial shift register state is 0 0, that is the initial condition. Now, input will be either a 1 or a 0, and so what happens is if the initial condition is 0 0 for the shift register, we are only focusing on the shift register and the input, rest all we have blanked out. Suppose the input is 1, then this 0 will go here, this 1 will go here, and the older 0 must be thrown out. So, after shifting in, this portion 1 has shifted here, the 0 here has shifted here, and the previous 0 has been thrown out, discarded. So, we drop the oldest bit. Okay. And we can do so for all possible combinations of input bit and the current state of the encoder. So, we did that example for 0 0. What if the 0 bit comes in? 0 0, what if 1 bit input bit 1 comes in? If the state of the encoder is 0 1, 1 0, 1 1. So, clearly there are 8 possible combinations. So, there are 8 entries into the table, and for each one of the input bit and the current state, we have a calculation of the output bit based on the original state of the encoder, which was as follows. So, whatever is the input bit, and we have an output bit going. So, let us look at this example a little bit more carefully. So, we have an input block, and then we have 2 bits as the encoder. We have this going in here, binary adder here, and this goes to your output. Similarly, you have a binary adder here, the input bit comes in here, and you have 1 here. So, N naught equal to 2 and K naught equal to 1. Now, if you were to look at the table, you will realize that whatever is sitting here, if it was a 0 0 here and a 1 comes in here, then this 1 shifts here and the older 0 shifts here and the last one is discarded. And once you have that, then these calculations can be conducted and you can do this basic calculation and it will give you the desired output, right. So, if we go back to our slides, and we will see that it is possible to generate a table of input bits, current state of the encoder and the output bits. Okay. Now, suppose if you look at the next slide, we can represent this as a simple state diagram. So, we can have the state diagram of the encoder in the slides. If you can see the state diagram, you have a 0 0 as one of the states, 0 1 as one of the other states, 1 0 and 1 1. So, we have only 4 states, and we can see that depending upon whichever state you are sitting in, if a 0 comes in, your state does not change, but if a 1 comes in, your state changes. If you are sitting in state 1 0 and if a 0 comes, you become 0 1, but if a 1 comes, you become 1 1, because the older bit will be thrown out, this bit will be shifted here and a 1 bit will be shifted in the first place. If you are sitting in 1 1 and a 1 comes, you will retain your location as 1 1, but however, if a 0 comes in, the older bit will be thrown out, the 0 will move in here and the older 1 will move to this place, leading it to a 0 1. Similarly, if you are at 0 1 and a 1 comes, then you will go to 1 0. So, you can make this a simple state diagram that you do for typical circuits. So, we go to our slide where we show that we have the state diagram for the encoder, this particular encoder, and this state diagram interconnections will change if I change the logic circuit. So, only 4 possible states are there, and we have already represents the bits associated with each arrow in terms of the incoming bits. So, it can be seen that the same input bit gets encoded differently depending on the current state of the encoder, and in this way this code with memory is different from the linear block code, which gives the same output for the same input. Now, if you look at the state diagram, the same information can be represented in a much more friendly manner using a trellis diagram. So, what is a trellis? A trellis is a graph whose nodes are arranged in a rectangular grid which is semi-infinite to the right, and therefore, this code is also called as a trellis code. The number of nodes in each column is finite and is limited to the number of states. So, let us look at the same example, the same state diagram now being recast as the trellis diagram. On the left hand side, we have the different states. As you know, there are only 4 states, 0 0, 1 0, 0 1 and 1 1. So, each of these nodes represent a state. On the x axis, we have the time axis, that is, each time an input symbol comes in, a state transition may or may not happen, but will move to the next level and the next level and the next level. So, initially we are at state 0 0 represented by level 1. Okay. Now, if a 0 comes in, you can see from your state diagram that you will retain your location in the state diagram as 0 0. So, you continue to be the top node is the 0 0 state. But if a 1 appears as an input thing, a state transition will happen and you will move to 1 0. So, there is an arrow connecting here. But please note, regardless of whether a 0 comes in or a 1 comes in, you can never go from state 0 0 to state 0 1 or from 0 0 to 1 1. So, certain state transitions are just not possible. The transmitter knows this, the receiver knows this, but the noise does not know. So, this geometric structure together with the algebraic structure will add to the strength of our trellis codes. Okay. This is the point to be observed, that we have now to our assistance a geometric structure as well.
So,
yes.
So, but we can design the logic circuit in such a way that it may jump from 0 0 to 1 1.
Okay. So, the question being asked is, can we design our circuit diagram to have a transition from 0 0 to 1 1? Sure you can, but please note then some other transition will not be possible, because there will be only two branches emanating from every node. Every node is a state. One branch should correspond to input being 0, other should be corresponding to input being 1. There are only two possible inputs, 0 or 1.
But for the 1 we can, for 0 it is going to next state 0 0, but for the 1 incoming bit it may go to 0 1 or 1 1, that is what I am asking.
Yes, it can be possible that we can have a connection between this node and this node, but then there will be no connection between this node and this node. The point is, no node is holier than the other node. For me, these are just 4 states, 4 nodes, whether it is moving from node 1 to node 2 versus node 1 to node 3, but it will not be able to transit from node 1 to node 2 and 4. So, some transitions are not legal. That is the point of this exercise. I know it, receiver knows it, noise does not know it. So, I will use this geometric structure also to help me reconstruct what was sent, and it will be used, the same trellis diagram will be used to decode the transmitted bit stream. It is an important observation. So, if you continue with this trellis diagram notion, then you will realize that for whatever state you are in, there will be two emanating branches, one for 0 input and one for one input. On the top of each branches is the output of the encoder written. So, since it is n not equal to 2, you will always find 2 bits written on every branch. So, this is a recast of the state diagram in terms of a trellis diagram. See, it is semi infinite, we know where it starts, it does not end until infinity. So, it continues to infinity, therefore, we call it semi infinite. So, we have noted that every node is a state, and then the rate is 1 by 2. So, 1 bit comes in and 2 bits go out. So, input bit can be 1 or a 0 corresponding to 2 emanating branches from each node. We can say that the top branch represents the input 0 and the bottom one represents input as 1, and so output of the encoder is written on top. So, this trellis diagram can be used to encode the input bit stream very easily, because we already have built in the time axis in there. It is not so using the state diagram, where we have the same information, but not represented in along the time axis. So, encoding is very simple. Encoding is just following directions along the trellis diagram. So, we start with the top left node. Now, if a 0 comes in, follow the upper branch, 1 comes in, follow the lower branch, right. So, in fact, the input bit stream say 0 1 1 1 0 0 1 is telling you go up down down up down along the trellis. So, if you look at this trellis diagram again, if you have a 0 comes in, we move here, 1 comes in, we go down, 1 comes in, we move down, 0 comes in, we go up down up, and we just read out whatever is written on top of that branch that we transition along, and that is the output. So, the input stream is just a direction that whenever you hit a node, whether you go on top or you go on the bottom. So, it is extremely easy to encode. It also shows a very important thing. Any particular bit stream to be encoded follows a path in the trellis which is unique. So, input bit stream is corresponding to a unique path in the trellis. There is no other way out. So, the decoding problem should be finding out the most likely path in the trellis, and that is what we will pursue. So, let us say we have to encode this random bit stream 1 0 0 1 1 0 1 dot 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 dot. So, we start with the top left, and the moment we hit a 1, we take the lower branch, 0 hit the upper branch, lower, lower, upper, lower. So, it is up down, and we can now look at the trellis diagram here. So, since the input was 1 0 0 1 1 0 1, 1 means down, 0 means, well, we have two options, go up, take the upper branch, take the upper root. Another 0 means of these two branches which are emanating out, please take the upper branch. Now, I have reached here and I look at the input stream, it says 1, take the lower branch, and it says 1, take the lower branch, because please note along the x axis is the time axis. As the input bit stream comes in, I follow the paths. So, I am sitting here, and now I again look at 0, I take the upper branch, and I get 1, I get the lower branch. And now I just read out what is written on top, because the encoder for that state and input is already pre-calculated. So, I read out 1 1 0 1 1 1 1 1 1 0 1 0 0 0, and that is my nice looking output bit stream. For 7 bits of input, we have 14 bits of output. It is not a surprise because the rate is 1 by 2. So, clearly any particular input bit stream is a unique path in the trellis that I have shown here. The red path is 1 0 0 1 1 0 1 input bit stream. Now, we have a very nice succinct polynomial description. So far we have considered pictorial representation in terms of state diagram and trellis diagram. We will now go for a polynomial description using a delay operator. Why a delay operator? Because it is very handy. We have already a shift register where every shifting operation is a delay operation. So, we already know that there is a 1-to-1 correspondence between a vector and a polynomial. We have seen that in earlier convolutional codes. We will use the delay operator in a similar manner. So, we will have, for example, this 1 0 1 0 0 0 1 1 with oldest digit to the left and the most recent digit to the right as it enters the convolution encoder. So, the analytical expression will be also sometimes referred to as the transform in terms of ID is the following. So, it is nothing but 1 0 1 0 0 0 1 1. The coefficients of d, d cubed, d raised to the power 4 etc. is all 0, they are corresponding to the zeros in the bit stream. The d is the indeterminate and is the delay unit. So, consequently, any sequence I 0, I 1, I 2, I 3 can be represented as I 0 plus I 1 d indeterminate plus I 2 d squared. So, it tells you where in the location in terms of time frame my bits are. So, we can have very efficient FIR based representation. What do you have is an input bit stream and of which k naught is the symbol frame, input frame, we have FIRs here and then linked to the output. These FIRs are nothing but memory and logic. Similarly, I can have a more complex setup. Here in example k naught is 2, as you can see, n naught is 4. So, the rate is 1 by 2 and you can have additional FIR filters. So, this is to illustrate that it is extremely hardware friendly. This is a solved problem. We can build very efficient encoders for convolutional codes. So, we just now saw an example of k naught is equal to 2 and n naught is equal to 4, but can we represent this encoder using a polynomial matrix or generator polynomial matrix? Well, the answer is yes. All we have to do is learn how to do an input output relationship. So, the largest degree of a polynomial which in this set of generator polynomial is m, and a block code, if you recall, was used represented using a single generator polynomial, but here we will have a generator polynomial matrix linking the input to the output. Okay. So, finally, we have to link say k naught input bits to n naught output bits through a delay register. So, let us look at a very simple example. It is our previous example. So, k naught is 1, n naught is 2, and then 2 elements in the shift register. But if you look at A, the output in this first bit, well, it takes the current bit, the previous bit, and previous to that bit. So, current, no delay, d raised power 0, 1 delay, d raised power 1, 2 delays, d raised power 2. So, this first one is linked to the input as d squared plus d plus 1. But if you look at B, the second output, which should be the second element of the matrix, it is nothing but the input d raised power 0 plus not the first delay, but the previous to previous that. So, d squared. So, d squared plus 1. So, all I am doing is relating the input to the output through the series of delays. Okay. So, this is the example how we input and output are related, A and B are related using the d squared. So, we have these two elements of the generator polynomial matrix G 1 1 and G 1 2 linking input 1 to output 1, input 1 to output 2, and so we have consequently the notion of a generator polynomial matrix, which we will now write as d squared plus d plus 1 and d squared plus 1. So, the entire hardware encoder can be represented using this generator polynomial matrix. So, if you give me the encoder in hardware, I will give you the generator polynomial matrix. If you give me the generator polynomial matrix, I will give you the hardware implementation of the encoder. Okay. So, let us look at another simple example. Again, we have 4 memory elements. Well, I first look at A. Hey, this A is nothing but the input, nothing else. So, it gives me a feeling that it should be just 1, and it is going to be a systematic convolution encoder, because the first bit goes right like that. The second is the parity. And how are we calculating the parity? Well, it is the same bit and XORed with 4 bits that came before in the bit stream. So, it is delay d4 plus 1. Okay. So, this is the generator polynomial matrix for this. So, A is 1 and B is d4 plus 1. So, we have the generator polynomial matrix representation as follows, and we can say that this is clearly a systematic convolution encoder. So, if you look at this example again, we have now input k 1 and k 2, output n 1, n 2 and n 3. Again we have 3 bits and we have clearly logic units. Please note, in this example we have interestingly put k 1 just going into this one. Okay. So, the constraint length will be defined with respect to only k 1. Please note, this 3 units in the memory is not a multiple of this k 1, k 2 and k naught equal to 2. So, now we have 3 outputs related to 2 inputs. So, there should be 6 elements in this. So, it is a 2 cross 3 generator polynomial matrix. Now, if you look at it, n 1 is nothing but k 1. So, it is just a 1. n 2 is directly linked to k 2. Looks like we are again in for a systematic convolution encoder. So, this G 2 2 is 1. Note n1 is no way linked to k2, so it is 0. n2 is no way linked to k1, there is no connection, so it is a 0. So, you have a small identity matrix right here, and here the fun begins. n3 is related to k1. So, G13 is now 1 plus a delay plus d cubed, because this is d squared d cubed. So, n3 is d cubed plus d plus 1, but n3 in no way is related to k2. So, there is a 0. So, just by visual inspection I can write the generator polynomial matrix. So, we will use visual inspection and immediately write the generator polynomial matrix. We are just trying to write the elements of ith row and jth column using the input output relationship. So, if no path exists, then it is 0, as we saw for G12, G21 and G23. There was absolutely no connection between say K2 and N3. And if there is a direct path, then it is unity, as we saw in G11 and G22, and thereby we got the identity matrix, and rest all is you have to just observe how many delays you are going through. So, with that we come to the end of this lecture. Let us summarize what we have learned so far. We started off with the definition of tree codes and convolutional codes. Then we found a very interesting pictographic representation of trellis codes using trellis diagrams. We learned how to use this trellis diagram to encode very efficiently an input bit stream. We also made a very interesting observation that any particular input bit stream corresponds to a unique path in the trellis. We then went on to define what do we mean by polynomial description of convolutional codes, and finally, we were able to represent any encoder in hardware using a generator polynomial matrix. With that, we come to the end of this current lecture.